This map shows the Arctic. The red dashed and solid lines show the drift track of the Norwegian ship Fram under the command of the famous scientist and explorer Nansen. The drift, which took place at the turn of the century, took 3 years to complete and yielded much valuable scientific information about the Arctic. More recently, in the spring of 1989, CEAREX Arctic was established to further our scientific knowledge of the Arctic using modern technology. Its 6-week drift is shown by the yellow line. What follows tells the story of OCAM.
Then we'll put up the frame, put up the insulated tent cover and the end walls, and we'll cut a hole in the floor and prepare the building for diving.
Being the sole representative from Maravilla, I claim this territory and all the ice under it for Aslan North.
CEAREX is an acronym which stands for the Coordinated Eastern Arctic Experiment. It's a project funded by the Office of Naval Research. The main thrust of the whole project is to study small and medium-scale processes that interchange heat and momentum and biological material in the ocean and cause an interchange between the atmosphere and the ocean. This camp is devoted largely to studying physical oceanography and small-scale processes related to these transfer mechanisms. We have a variety of experiments here. We have a large number of experiments designed to study the way in which internal waves in the ocean transfer energy vertically and how waves are generated by motion of the ice over the ocean surface. We have several experiments that deal with studying turbulence in the ocean, and we have a meteorological program to study how the atmosphere exchanges momentum with the ice. There are a total of about 24 investigators out here on the ice. We have 14 prefabricated buildings, and in each building is an individual experiment that represents an attempt to get some sort of picture of these different processes.
When you look around at this fantastic landscape and imagine the forces that must have caused this topography, it's hard to imagine that we're standing on one of the calmest, gentlest oceans in the world. The reason the Arctic Ocean is so calm is it's cut off from the influence of the atmosphere for most of the year by this layer of ice. The only way the atmosphere can really make much of an influence on the motions down below is when the wind blows, it drags the ice along, and the bottom of the ice has a topography that's much more exaggerated than the top, and the features on the bottom leave a wake of internal waves in part. And we're in the business of trying to see how the influence of this motion propagates down deep into the Arctic Ocean. When you think about it for a minute, the best way to track the vertical propagation of waves is to have instruments, say current meters, at a whole bunch of different depths. But this is a real trick in the Arctic, because if you hang a current meter down on a string, you need to know which way it's pointed, and so you put a compass in it to tell which way the instrument's pointed. But compasses don't work very well in the Arctic, because the magnetic field is mostly pointing straight up and down. If you're at the North Pole, getting the compass to point north would be a real trick. What we've done is build a Doppler sonar. This is a device that shoots out beams of sound in 4 different directions. The sound goes down, scatters off the plankton that are drifting in the waters here. And the plankton make a rather weak echo, which comes back to the instrument. We detect the echo and measure the Doppler shift. And this gadget is brand new for us. We're just getting it wired up for the first time. It shoots sound out at 160 kilohertz, and the typical Doppler shifts are 1 or 2 hertz, about that, and that's what we try to detect, and that corresponds to 2 to 4 centimeters a second of water motion. The nice part about the gadget is once that you have it oriented in the bottom of your hut, you know which way the sound beams are pointed all the way down 400 meters into the sea, and so one compass or a solar navigation, a celestial navigation for which way it's pointed, will do the job of telling you which way the velocities are for the top 10th or 8th of the polar ocean. What you see appearing are 4 different fields of color slowly crawling their way up the screen. Each field represents the velocity seen by one of the 4 sonar beams. We have a north, south, east, and west sonar beams. And for each beam, the surface just below the ice is on the left, and toward the right, with each tick mark, you go down another 100 meters. So we're about 550 meters down by the right side of the field. As the beams crawl up, you see for each reversal of the black and white bars, another hour has gone by. And the colors you see represent the velocity of the ocean down beneath us, where the blue color corresponds to currents toward the sonar, and red away. And you can see there are mirror images forming. We're getting really clean data down to about 300 meters. The last few hundred meters, the echoes are so weak at this point that the measurements aren't very good, but you can get a sense of what the currents are. Our hope in coming here that we would not get a number of hours, but more like a 30-day continuous run. The instrument is brand new, and my guys have just a few more days of getting the last glitches out of it, and we'll let fly and hope for the rest of the month we get a long continuous record like this. You can see the big currents which appeared and lasted for about 4 hours and then died away as 1/2 cycle of an internal tide, which is seething along underneath us in the ice several hundred meters down. If the record had persisted for a number of days, you would see the red, blue, red pattern oscillating rather rhythmically and also propagating vertically.
Since we're standing on a floe of sea ice that's only drifting on the ocean, it's free to rotate as it's subjected to the various forces. And so the question becomes, which way is a given direction? For instance, true north for all the instruments to be surveyed into. And for that we use a venerable instrument, a theodolite, to do a sunshot. It's still in this age of satellites being the most accurate way to get a measure of direction once you're on the ground, given a known latitude and longitude, of course. What we have here is the baseline or camp azimuth established from that hut in the distance, and in fact specifically it's from a point on the black stovepipe where it comes out of the building through the axis of the theodolite, and that corresponds to the camp azimuth. By taking sunshots 2 or so times a day, I monitor the true direction of that axis, and all the rest of the instruments of camp are then surveyed into the sunshot readings I get from the theodolite. It's a good idea to work up a sunshot immediately after you take it, so if you discover that you've made some error in observation, you can immediately take another one to correct it. And also, it gives an indication if, in fact, the flow has suddenly rotated. That's something of interest to quite a few of the observers out here. This is a form that's been developed and we've used for quite a few years to simplify the calculation, and so that the step is the same each time, and thereby systemic errors don't creep in. And the calculator works up the site reduction and gives me a true azimuth of the sun of 179.19 degrees, from which I subtract the horizontal circle, which is the angle on the theodolite at the observation time between the baseline and the sun, to give me a true azimuth of the reference line of 242.17 degrees.
We are out here on this ice camp operating two A-Stars French machines. We have an operation here which requires transportation of scientists, equipment around in the area, medical transportation if it's needed, and at least not to forget the transportation we might get here if the ice breaks up, and the camp is going to be divided into several parts.
Basically have the CTD instrument on the end of a wire going up and down. Depth is read off through a computer interface, and the computer keeps checking the depth, and when a predetermined depth is reached, it turns the winch around and brings the instrument back up to the surface. In this case, we're cycling between 5 meters depth and 400 meters depth. This plot shows both temperature, which is this line, and salinity, which is this line. This profile tells us really quite a bit about what the conditions are at this site. The top layer, you see, is about 100 meters deep, and that's the mixed layer. The temperature in the mixed layer is minus 1.87 degrees, and that corresponds to the freezing point of water with this salinity. Salinity is about 34.13 or so. The water we see down, well, centered at 200 meters is quite a bit warmer. It's 2 degrees C, and we know that that water comes from the Atlantic Ocean. It's the water that really supplies all the ocean heat to the Arctic Ocean. It's all Atlantic water that comes in through Fram Strait. And so I think what we're seeing here, that this is an area where the Atlantic water is interacting vigorously with the surface and with the ice, and is losing heat through turbulent mixing in the mixed layer. With With water temperature and salinity, we can calculate the water density, and this plot is the sigma T over the same 600-meter depth range, and shows that at the base of the mixed layer the density increases dramatically. Basically, this is the sharpest part of the sharpest stratification in the upper ocean. The little dotted line is the Brunt-Weissler frequency, which is basically proportional to the square root of the gradient of this density profile, is a characteristic frequency of the internal wave field in the upper ocean. The CTD samples 24 times per second, and it's going about 70 centimeters a second downward, so we get a sample every 3 centimeters or so. And we're able to actually plot these variables at a pretty high resolution. In this case, we've taken half-meter bin averages of temperature and conductivity and plotted those. So this line on the left is the temperature again. Conductivity is this line on the right. The interesting thing about this profile, it didn't show up in the larger scale plot, are these step-like structures. And again, that seems to be characteristic of the mixing process. There's two things that are going on here. Seems to be a high level of turbulence at times, and there's also the process of double diffusion, which creates these layered type structures. The interesting thing is that the Arctic Ocean is salt stratified. Most of the open ocean is stratified by temperature. In other words, warm waters at the surface and cold waters at depth, while the Arctic Ocean is stratified by salt. In that sense, it's called a Mediterranean Sea, which it's unique in being like the Mediterranean and being stratified by salt content rather than temperature.
Hi, I'm Murray Levine, and I'm here from Oregon State University with my partner Clayton Paulson, and we've come to the Arctic to measure internal waves below the Arctic ice cap. The reason for coming to the Arctic is to measure internal waves is for two reasons. First reason is that the ice cap provides a very nice stable platform to measure the internal waves from. It's much more stable than from a ship. Second reason is that the Arctic Ocean seems to have internal waves that are quite different from those found at temperate latitudes. The internal wave energy seems to be much smaller, and we're up here to try to find out why. What we have here are three traces, plotted conductivity on this axis and time on this axis. Time axis covers a little over 10 hours of data. The three traces are from different depths. The bottom trace is from 50 meters, then 80 meters, and 100 meters. The feature that stands out the most obvious is these oscillations, and these oscillations are due to internal waves that move the water up and down vertically, causing the conductivity to change at a fixed depth. You can see the period here of these waves is of order 1 to 3 cycles per hour. As you get closer to the surface, down here at 50 meters, we don't see any of the oscillations. The reason for that is that there is no stratification in the water at 50 meters. So even if the water were moving up and down, we wouldn't see the signature from a fixed sensor depth. On this computer, we're recording the output from an acoustic Doppler sonar that's mounted directly below this table, drilled through the hut floor and then through the 6 feet of ice below, and is mounted in the hole, pinging downwards to about 250 meters depth. The velocity profiles will tell us something about the internal waves that are going on below the ice and complement that conductivity record that we just looked at. This will tell us about the horizontal velocity features, whereas the conductivity record told us a little bit about the vertical displacement of the water column. Here we have a display of the output of the Doppler sonar. What we have is a plot of depth this way to 250 meters and velocity plotted across the top. Zero velocity here, plus 25 centimeters and minus 25 centimeters a second here. The green trace is the plot of the north-south velocity. The yellow trace is the east-west velocity. The white trace is a measure of the backscattering strength from the acoustic Doppler. You can see that decreases with depth. The velocity profile is fairly uniform in the upper layer. That's the well-mixed layer. And here we see another trace coming up after a 1-minute average. It's fairly constant with depth. Then below the mixed layer we see there's a large shear shown in both the green and yellow profiles. Below the mixed layer we see more vertical variation. Here you can see in the yellow profile especially there's a lot of oscillation with depth. That variation is in part due to internal wave signature, and we expect that as we watch this in time over several hours that we'll see that these oscillations propagating vertically.
I'll remind you that this is the domain of the polar bear. Their appearance is basically totally unpredictable, and when you go out around camp you should keep that in mind. Don't become complacent. If you're going to go out of camp on, say, a ski trip or something like that, tell us where you're going, take a flare gun, a rifle, tell us when you expect to come back, and try and stick on your direction or itinerary so we know where to come look for the shred. When we talk about the general area of camp, we're talking about sort of peripheral buildings. If you leave and go out to the runway, let's say where we're loading and unloading, that's probably a reasonable safe place. But I think the question you have to ask yourself is how fast can I run to the nearest shelter? And in particular, if you're going to be working around some of the pressure ridges out there that would afford cover to a polar bear, then you certainly ought to have a weapon with you.
We're looking at the boundary layer beneath the ice. That's the layer of water which effectively couples the movement of the ice to the movement of the ocean beneath. What we've done is to set up 3 stations like this. At each station we have acoustic transducers mounted on a little bar, and these transducers at appropriate intervals transmit a signal. The signal through any vertex of the triangle is received by the hydrophones at the other 2 vertices. And the signal travels in both directions. That's to say, after transmitting from here, another signal is transmitted from the other end. By measuring precisely the time that the sound takes to travel along the path, we can measure small differences which are caused by fluctuations in the temperature or fluctuations in the flow speed, and we can separate those contributions. The problem that we're analyzing is somewhat analogous to that when light travels through the atmosphere and appears to fluctuate, for example starlight that scintillates at night.
The ice here is about 2.5 meters thick. At the bottom surface of the ice is in contact with the ocean surface at approximately 0 degrees C, and the top atmosphere now is at about minus 35 degrees C. So that means that there's a range of temperatures through the ice. We have thermocouples positioned every 15 centimeters from the top of the ice down to the bottom. And we measure the temperatures at each one of the thermocouples at these temperature junctions with a digital thermometer. The temperature of the ice will change perhaps a couple degrees, 4 or 5 degrees, over the period of a month.
And I'm the meteorologist on this experiment. Right now I'm getting ready to launch a weather balloon. It's called a Ray-Winson. This device here measures temperature, humidity, pressure, and the winds as it goes up in the atmosphere. It goes up about 10 kilometers and transmits the information by radio using this antenna here. This long string here is an Omega navigation system antenna, and from the position of the Ray-Winson we calculate the winds in the upper atmosphere.
are many phenomena which cause strain and tilt in the ice to occur. For instance, the cracking of the ice that precedes lead formation will lead to a strain field being built up in the ice. However, our primary interest at this ice camp is to study the effect of internal waves and surface waves on the ice and how these phenomena cause the ice to tilt and strain. This is an example of one of the strain meters we've deployed in the ice. This instrument is 1 meter long from here to here, and it's rigidly attached to the ice with these bases at either end. Inside the instrument is a 1 meter long Invar wire. As the ice strains, this wire stretches and the signal is sent back along a hard wire to the hut where the electronic recording system registers the signal. This 22-minute long strain meter record shows two predominant waveforms. The higher frequency waveform of about 25-second period wave is the so-called flexural gravity wave. These waves travel for hundreds of kilometers across the Arctic pack ice and derive their energy from the open ocean swell impinging on the ice at the ice-ocean boundary. The longer period wave is the response of the ice to the internal waves forcing the ice to go up and down from below. The longer period wave here is of order 20 minutes long, which is the Weissler frequency at the thermocline. In order to determine the directionality of these waves, we deploy rosettes, each consisting of 3 strain meters. In these rosettes, these strain meters are orientated at 120 degrees to each other.
And I'm here measuring tilt fluctuations of the surface of the ice in conjunction with strain measurements being made by the Scott Polar Research Institute. The hope is that by measuring tilt and strain simultaneously on the ice, we can learn better how waves propagate through the ice cover in the Arctic Ocean.
We're looking at the bio-optical properties of the ice and the water, and now we're looking for the particles in the water. And we're expecting those particles at the under ice surface, as we can see in this chart of the surface properties of the ocean, in the mixed layer, and at the bottom of the mixed layer where we have a picnic line. Now Roger has just plotted this CTD profile that shows the density discontinuity at about 92 meters. And so we're going to send our water bottle sampler down just to this depth. This is a simple Niskin bottle, and the bottle is going to go down on the wire, and a messenger will be sent down the wire. It'll hit this white rod and open this key, release these 2 plungers, and they'll enclose the sample of water in here. Then we'll recover the bottle.
This morning we were deploying the spectroradiometer under the ice, got it through the ice hole, and then moved it so that it faced up to see the downwelling light that was coming through the sea ice.
Applied Physics has developed a autonomous underwater vehicle, or AUV for short, that has been designed to carry a CTD, conductivity temperature depth instrumentation, underneath the ice in the Arctic ice cap. The vehicle is approximately 62 inches long with a 3.5-inch hull. It is a completely autonomous vehicle, contains a tracking transducer, a homing hydrophone, conductivity cell, and a temperature probe inside the conductivity cell. This is a port for the pressure transducer. Working our way back, contained in this section are the electronics for the conductivity temperature depth instrumentation. Working back, are the electronics for the active guidance and control electronics, the homing electronics, and the power amplifier for the tracking transducer. Also, a lithium battery pack is used to power all the electronics and the motor. In the aft end of the vehicle We have obviously the propeller and two coupled vanes, one elevator for depth control and the rudder obviously for directional control. There's a port in the tail that's used for external communication for vehicle configuration and also used for extracting data out of the instrument after the run. Also a pressure port where we use to pull a vacuum to make sure there are no leaks with the O-rings. And I also neglected to mention that there is a triax flux gate compass located inside the nose, which is used for direction heading sensor. The vehicle is programmable via a personal computer, and we use a menu-driven program basically where we can select various run geometries, depth, direction, time, duration, and we program the device prior to launch to run a particular course. After the end of that run geometry, the vehicle enters a homing phase, and a synchronized acoustic beacon is used to home the vehicle that the vehicle will home to.
More exciting. Okay, we're crossing that mark at 7:20. Geez, we're like 18 seconds off. That's awesome. That's great. See, I have us crossing the north-south line at 7:20. That's great.
The vehicle will be launched pre-run by itself at a certain length of time that's programmed into it, and then it will turn into what we call a homing mode. It will home on the beacon, which is down in the hold. There's an acoustic beacon that gives off a signal. The vehicle will home on that. When it gets close to it, it shuts down the engine and floats up to the ice. The diver's job will be to go in and recover that vehicle. That's what you see going on here, preparing for the recovery. Right here. Come on, I'll bite yours. I guess that's okay. I need to shoot those. One of the requirements for diving operations, obviously, is if there's an accident, we need to be able to fly them out of this ice camp and back to a recompression chamber. So before we can commence a diving operation, we have to know the weather at both ends, the weather here at the ice camp and the weather in at Longyear or whatever evacuation center we plan on using. So much for that dive.
This is ridiculous. We've got to get him in the water center. That's nuts.
Do I go down and take a picture? Sure, go down just a minute. Launch recovery vehicle is recovered. Over.
We've now moved the hut over the hydro hole that we made the other day and installed 4 receivers 10 meters from the hydro hole around the hut below these tripods. We insonify the water column below the hut from the hydro hole with very brief acoustic pulses and receive the backscattered energy in the receivers and measure the Doppler shift of that backscattered energy, allowing us to estimate the 3 components of velocity down to about 10 centimeter scales to a depth of 30 meters. On the screen in front of us, we're monitoring the Doppler shifts from 2 of the receivers, one north and one south of the camp, between the depths of about 10 meters down to 25 meters. And this shows the deviation in Doppler frequency from 0, with about 4 hertz per centimeter per second corresponding to the component of current in that direction. The red, as you can see, there's a symmetry about 0 showing that there's a mean current north and south, and the other 2 traces here show the coherence of the backscatter as a figure of merit to allow us to know how much of the backscattered energy actually represents a coherent backscatter process. And the hope is that we'll be able to well resolve the turbulent processes below the ice layer using this information.
My interest in this project is studying turbulence in the boundary layer under sea ice. The principal instruments we use are these clusters of small mechanical current meters, which we sample at about once per second or faster, combined with a conductivity temperature sensor, which if, for example, we should drift into ice that is melting, we would be able to measure the heat flux with it. We've been doing this kind of work for some time in the Arctic, and we've had quite a bit of success at actually measuring the stresses that are put up, that exist between the ice and the ocean. as the ice moves across the ocean forced by the wind.
My interest in the Arctic is to look at the fine-scale variability in the ocean in the upper 350 meters. The sensors are located at the bottom edge of the instrument. What we have on this two shear probes, the two white probes here, which measure the microstructure velocity signal in the ocean. At the same time, we're measuring with this sensor here the fine-scale temperature fluctuations which are occurring as the instrument profiles downwards. A further sensor is located a little further back here. It's a conductivity cell which is designed to give us a measure of the salinity of the ocean at the various depths that we're profiling through. We're measuring 8 variables. The orange and the purple line are measures of the microstructure shear. The grey line here, which is just sloping up at a constant rate, is a measure of the pressure, which is a measure of the depth that the instrument's presently at. There are 2 lines here almost laid on top of each other, which are the 2 independent measurements of the temperature. Further measurement of the conductivity is the green line, and then we have a couple of other variables that are related to the gradients that we see that are located roughly along the 0 line here. At the moment, the instrument is falling through a patch of water where both the temperature and the conductivity are increasing with depth in this region here. In the first 70 or 80 meters near the surface, these variables are almost constant. The large purple spike, which is associated with one of the shear channels, we believe is associated with the impact of the shear sensor with biological matter in the ocean. Now, as the trace progresses, we see that we're getting down into an area where the temperature is much more irregular, and we are in fact getting down into water which can be associated with the inflow of the Atlantic layer water into the Arctic Ocean. In the shear records, we see that near the surface there is a large variability in the shear signal, which is indicative of turbulence occurring. And the turbulence near the surface is there because of the friction of the upper layer water on the bottom of the ice. Lower down we see another patch of high variance in the shear, which is again a turbulent patch associated with some local increase in the large-scale shear at that depth. As we watch the trace further, we'll see that these temperatures, the 2 blue lines, reach a maximum, which, as I said before, is related to the Atlantic layer water coming in through Fram Strait. The temperature will then decrease as we go to greater depths.
So our program is to stick a sonar down beneath the ice. It shoots a narrow beam of sound energy up, and the sound energy is reflected off the side of the mountain, if you will, back to the sonar device, and we record the travel time for that event. And we do that for every direction here at every distance.
Most of the Arctic doesn't have a very good record, basic hydrographic record, and there are very few records that cover many seasons, and that's mainly because ships don't drive around in the Arctic. We devised some buoys which employ temperature and conductivity sensors attached to a wire that hangs down 300 meters into the ocean. The wire is suspended from a aluminum tube that is about 4 meters long and penetrates the ice and floats at the water surface. Inside the buoy tube, there are electronics to take data from the signals, from the sensors that are then converted into a digital format and transmitted through the Argos satellite system. And the Argos satellite system also provides a positioning of the buoy so that we know where the buoy is when the measurements are made. After it's in, the buoy will float around for periods up to 2 years, and it transmits data from each of those 6 sensor pairs every 12 minutes. So over the course of a couple of years, the buoys produce quite a bit of data.